We're going to have a quick look at hoteling. So it's the cake thing, yeah? And we're going to derive this rule a bit more rigorously. Okay, so we're going to think of a profit maximization problem for a cake owner. And there's lots of other cake owners. Okay, so it's perfect market, but the total amount of cake is fixed and limited. Okay, so what's the problem for a given cake owner? So the given cake owner wants to maximize profit, doesn't it? By choosing R for all time, if we want. We can write it like that. And what is that profit? It is the integral of, so if we have the big model, we call it like W, oh, let's do it, WR T RT dt. That's revenue, isn't it? Is that correct? Not really. Because we need to allow for the discount rate. Remember, we're assuming this fixed constant discount rate rho, or interest, which is the same as the interest rate of the bank. And it means that future revenue is not as valuable as current revenue, because current revenue you can put in the bank and it'll grow and be more in the future. So this is what the net present value of total revenue over infinite time now. And we want to maximize that subject to the constraint. And what's the constraint? It's minus lambda, which is the shadow price of the stock, times the constraint, which is that ST. So the constraint was that ST is greater than or equal to the integral between 0 and infinity of RT dt, right? So ST minus the integral between 0 and infinity of RT dt. So we're going to assume that the constraint is satisfied with equality, that in the limit of infinite time you're going to use up all the stock. Why would you not do that? Okay. So, how do we deal with this? Well, what's the first order condition? I kind of realized I haven't done this in the course previously. I've done it in discrete time previously. But let's try this and see how it works. Okay. So we're going to take a first order condition in RT. Some arbitrary t, yeah. And what do we get? So how do you differentiate these integrals? Well, the integral is some curve, isn't it? And this is time, and the integral is the area. What happens to the area if at some particular time you raise RT? Well, it just goes up by the amount that you raise RT by, doesn't it, at that time. It's very, very straightforward. So, but, yeah, sorry, multiplied by this stuff. So, we just treat this, if we think of this as a sum of lots and lots of terms, there's only one term which has the exact right t in it. The others all have other t's. So if we just focus on that term, it's e to the minus rho t wrt rt. When we differentiate that, we just get e to the minus rho t wrt. And it's the same thing here. So I got the sign wrong here. Plus lambda. And this one goes, when we differentiate the right RT, it just goes to 1, yeah? No. Yeah, I changed this, so now it's minus lambda. Okay, so lambda is e to the minus rho t wrt. Okay, so what is, if we differentiate this whole thing with respect to t, what do we get? We just get naught. So lambda is constant, yeah? Lambda is the shadow value of the stock. It's just something, an unknown, but it's constant. So naught is differential of this with respect to time. So what happens to this term when we differentiate with respect to time? We get minus rho times what we started with, yeah, which we call lambda. What happens to this when we differentiate with respect to time? We get the WRT by dt. So actually, yeah, maybe no. So what's WRT dot? Sorry, just 2 seconds later. I screwed up here, didn't I? Because it's not just WRT dot, it's WRT dot times e to the minus rho t. So maybe in this case, it's easier if we just differentiate in the more standard way, and we just say it's minus rho e to the minus rho t WRT plus that equals naught. So then when we rearrange this, we can cancel those and rearrange, and we end up with WRT dot over WRT equals rho. Okay, that is hopefully